Hello. So in this video, I'm just going to kind of do a presentation on the first half or first part of my thesis. So it's titled A Self-Supervised Foundation for Automatic Respiratory Sound Analysis. So my supervisors are Dr. Hao Shui and Dr. Flora Salim. Okay, so this is kind of the presentation outline. First 5 parts are the real meat of the presentation, and then I have a little Q&A section at the end. But since this is a video, you can leave any questions in the comments. So in this first section, I'm just going to give an overview of my thesis topic, as well as cover some core concepts that are required to understand it. So automatic respiratory sound analysis. Let's break that down. So respiratory sounds, what are those? They're any sounds made by the respiratory system. So these can kind of be grouped broadly into 2 different categories. First, there are lung sounds, which we would kind of listen to using a stethoscope. So, the doctor puts a stethoscope here, and we can listen to that. And there are also voice sounds that are produced more up here that can be recorded by a microphone. So I'm particularly only interested in voice sounds for my thesis. And in particular as well, I'm not interested in speech. I'm interested in voice sounds that are non-speech. So what are these? Things like coughs, wheezes, breathing noises, stuff like that. And also, automatic respiratory sound analysis is a bit of a mouthful, so I'm going to be using the acronym ARSA for the rest of this presentation. So ARSA, it's a pretty broad term, and I've kind of collected a few tasks within this umbrella. So the first and most obvious one is disease diagnosis. We want to be able to automatically detect if someone has a disease based on an audio recording. So in this first paper up here, researchers have used it to detect COVID-19. Other researchers have used it to detect tuberculosis. And also this third paper here, researchers have used it to detect pertussis, also known as whooping cough. Another task is called cough segmentation. So you have an audio recording. What you're trying to do is find at which timestamps in that recording a cough occurs. So this paper did that using an ARSA system. Another one is cough classification. So sometimes medical practitioners will classify coughs based on their properties. So one way to define a cough is whether it's a wet versus a dry cough. So this paper built a system that was able to classify a recording based on whether or not it was wet or dry. And also you can use it for severity classification. So with asthma, sometimes doctors will use this scale to just kind of describe how severe it is, how intense it is. So this researcher built an asthma severity classifier using an ARSA system. So there are a lot of different potential tasks that you can use. There's a lot of things you can do with respiratory sound recordings. And what are the benefits of doing something like that? Well, just take the task of COVID-19 diagnosis, for example. One way you could do it is you have the patient go into the doctor's office. Doctor would have a stethoscope, listen to it, and that's called auscultation. And by listening for abnormalities, stuff like that, the doctor will be able to determine whether or not you have COVID-19. But there are some obvious issues with this. There's a reason why we don't really do that, at least in Australia. And it's that COVID-19 is highly infectious, and many respiratory diseases are pretty infectious. So if you're able to just get a diagnosis by coughing into your phone, then that's obviously much safer, and it's also much lower cost, because when you go into the doctor's office, you're taking up the time of a highly trained professional, whereas if you just cough into a smartphone, it's very low cost. It just sends it to a server somewhere, so it's in the orders of probably cents. Okay, so I'm going to just briefly cover what a typical smartphone-based ARSA system would look like. So smartphones, they're edge devices. So this would also involve, you could do this with other edge devices, like maybe an Apple Watch. So first you would cough into your smartphone, while recording this, and the first thing it will do is digitize that recording. So this is a sound wave. So on the y-axis we have the sound pressure, and on the x-axis we have time. So we're kind of measuring how does the sound pressure evolve over time. So that's kind of the raw data basically. But often with machine learning, we wanted to do a process called feature engineering, which is where we transform the data into a form that's more amenable to machine learning algorithms. You know, it plays nicer with them. So by far the most popular one for audio data is spectrograms. So there's a kind of a whole family of these types of transformations, but the gist of it is that it's a time frequency representation. So previously, this sound wave is just a time representation. A frequency representation is where you look at the frequency components of the sound wave, and a Melch spectrogram kind of is the best of both worlds, where, you know, frequency representations, they're very useful for analyzing periodic events, but using a spectrogram, you can also see how the frequencies evolve over time. So on the y-axis here, we have all of our bands of frequencies. The color kind of dictates the amplitude of that frequency's sine wave at that particular time block, and you can kind of see how that evolves over time. So we've got our Melch spectrogram. We then, or any feature or any like engineered features, and then we would pass that into our machine learning model. So one really cool thing actually is that because we've generated an image with a spectrogram, we can actually use a lot of techniques from computer vision. So a lot of CNNs, convolutional neural networks. So that's just something very interesting to note. But you can really use any model, to be honest. And then that would give you some sort of prediction based on what task it is. So for example, COVID-19 diagnosis, that would be probably a probability of how likely the person has COVID-19, and that would finally be displayed on the smartphone. So the key challenge of this area is what's called data scarcity. So I've kind of broken this down into 4 sub-problems. So data scarcity is just, there's something limited about the data sets that we're using. First is sample scarcity, which I've defined as simply there's just not enough samples in the data set. Next is label scarcity, which is maybe you have a lot of samples, but you don't have many high quality labels for them. After that is metadata scarcity, so there's a lack of useful metadata for all of our samples. And finally, class imbalance, which is there's a lack of particular types of samples. So in this next section, I cover the research problem that I'm going to be tackling in my thesis. So we've already covered that ARSA systems are very useful if we're able to build one because they're safe and low cost. But the key challenge is data scarcity. So when we have very limited data, we have poor predictive performance. It doesn't generalize well, which means that maybe it works well while you're testing it in a lab setting, but once deployed into the real world, it doesn't live up to the performance. And then limited data also can lead to very unreliable evaluations of your models. So in this thesis, I'm going to explore different methods that we can use to alleviate these data scarcity issues for ARSA systems on smartphones. So this next section is my literature review, and I kind of broadly explore 3 different areas. First is data scarcity in ARSA systems. So what kind of problems do we have exactly in ARSA? Then I kind of look at what techniques researchers have used in ARSA to overcome these problems, so data efficient techniques. And finally, I look more broadly in the field of machine learning to see what people have used, what data efficient techniques people have used, so that maybe I can bring them in and apply it to this area. So the first section, I'm just looking at data scarcity. So the first type of data scarcity I'm calling sample scarcity. So with machine learning, and particularly deep learning, we need a lot of data for training. And also, you also need a sizable test set to be able to reliably evaluate your model. So as you can see, so I've collected a lot of different papers and kind of just looked at how many samples that they've used for training and evaluation. And with the exception of COVID-19, the number of samples are extremely low. So, if we look at tuberculosis, there were only 38 samples used for both training and evaluation, which is far too small to train a model this complicated. It's like audio data, it's very complex data. And asthma, like this one, there's like 5 different diseases, but you've only got 38 samples. So very, very low number of samples. And to exacerbating this is that many of these data sets are not openly available. So other researchers can't even use data collected elsewhere. And while there are like some fairly big data sets, COVID-19 sounds, there were 53,000 samples, or over 53,000 samples, but these large data sets have issues of their own. So here's here are the actual papers if you want to kind of look at where these come from. So we have these big data sets for COVID-19, but there are some issues, which is label scarcity, which again is the lack of high quality labels. And for COVID-19, there are for all disease diagnosis really, there are 3 levels of labels. The first is COVID-19 sounds, COSWARA, these really big data sets, COSWARA, COFVID. They all rely on self-reported labels, which is the person would cough into a smartphone app and then they would report whether or not they were actually sick with that disease. And there are obvious low reliability issues with this. The next level up from this are expert annotated labels, where a doctor or someone with similar medical training who they would listen to the audio recording and they would say whether or not the subject of the sample had the disease or not. So this is much closer to how we normally detect these kind of diseases. It's very similar to auscultation. But again, this isn't perfect, but it's better, but it's also more expensive. And then finally, we have clinically validated labels, which is we actually do some sort of clinical tests. So for COVID-19, that would be a PCR test to validate whether or not the subject had that disease. So this is the most reliable, but it's also the most expensive. So we can kind of see there's a trade-off between how reliable the labels are and how expensive they are to collect. Another thing to note is that if we want to build a real disease diagnosis system in real life, we need to be able to differentiate between different diseases. So this paper noted that one big issue with a lot of these ARSA systems, particularly for detecting COVID, is that they're only concerned, the data sets only have a single label, whether or not the person had COVID or if they were healthy. And the problem with this is that we don't know whether the models are just picking up on the fact that the subject is generally sick versus if they actually have COVID-19, which is an issue, right? Because different diseases require different treatments. So it's very important to be able to detect exactly which disease the subject has. So in order to build a real-world system, we need training samples that have labels for essentially all respiratory conditions, so that we're able to differentiate between them, which is very, very difficult to collect. The next type of data scarcity that I'm going to cover is metadata scarcity. So metadata is very important particularly for the evaluation of ARSA systems. So one type of metadata that we want is a subject identifier. So for each sample, we want to know maybe not necessarily who it is, but at least being able to know which samples came from the same person. So this paper did experiments to kind of show that if you ignore subject identifiers, then it can lead to overly optimistic performance evaluations, because the model will pick up, it will start being able to just recognize the subject rather than recognizing the actual disease. So it will just kind of remember, this kind of sounds like that person, and that person had that disease. So therefore, all samples of that person would have that disease. So it's very important to be able to identify subjects so we don't kind of have that leakage into the test set. Next is time since infection, which is very useful metadata. So, a sample where the person was sick 2 weeks ago, but maybe they're essentially all better now. Maybe that's not too useful for us. And finally, demographic information. Having this allows us to kind of stratify our test sets and gives us better evaluation, even if our test sets are a little bit smaller. And finally, the final type of data scarcity I've identified is class imbalance. So disease diagnosis, again, for example, is a classification task. We're giving a probability of whether or not the subject has that particular disease. So medical data sets tend to be heavily imbalanced, as this paper notes as well. And the vast majority of samples come from healthy individuals. So the problem with this is that you potentially have too few samples of the minority class, usually samples of people actually being sick, that there may not be enough information in the training set for the model to actually learn to detect this class, and which is quite problematic because the minority class is usually what we're more interested in anyway. So those are kind of the four issues that I'm trying to tackle in this thesis. So the next section is I'm going to look at what data efficient techniques we can use to overcome this. So the first type of data efficient techniques is called data augmentation, and this is when we apply transformations to our data set to somehow improve performance. So the first, this first one is sampling approaches. So for example, we can use bootstrap sampling, which was used by this paper, and that's basically where we generate more samples by taking, for example, in this one, what they did was they have their audio recordings, but they would take segments of that and kind of turn that into more training samples. In this paper, what they used instead was a technique called synthetic minority oversampling technique, more colloquially known as SMOTE. And this technique basically it's an unsupervised algorithm that generates synthetic samples of the minority class, which can improve generalization. The next data augmentation technique that I've seen used in ARSA systems is called mix-up. So this paper used that, and it's a pretty cool technique. So basically what it does is that at each training step, a pair of samples are interpolated. So the features, the input data is interpolated. So you can see that here. These are two different training samples, and they've been kind of combined, and their labels have also been combined, and this is used as training to train the model. So this has been shown to improve generalization. Another technique that was used by this paper is introducing extra noise to the training samples. So what this is trying to solve is that there's potential bias in the environments of the recordings in our test set. So maybe they were all recorded in similar places. Maybe they were all recorded in a hospital. So this is not. So this makes assumptions, I guess, that may not hold true if we deployed this system in the real world. Maybe people are using this system, out in a park, or they're in their room. So what they've done here is they've added some ambient noise to all of the training samples to improve generalization. Another technique is called spec augment, which was again used by this paper. So going back to our mel spectrogram, we have our frequencies here and we have our time here. So spec augment is a technique from automatic speech processing, and it's been shown to improve generalization there. And what it does is it'll mask certain frequency bands and also certain time steps, and to hopefully improve generalization. Okay, so the next broad category of data efficient techniques I'm going to cover is transfer learning. So transfer learning is when we leverage data from a related task or domain to improve performance. So the particular type of transfer learning I'm going to be looking at is called sequential transfer learning, and that has two phases. You first have a pre-training phase and an adaptation phase. So say the task that we're trying to solve is COVID-19 diagnosis again. That would be our target task. So COVID-19 detection is our target task, and we would have a data set for that, that's called our target data set. But maybe we also have a second data set that's kind of related. That would be called our source data set, and whatever task we use to train on this is called our source task. So here I've kind of collected a kind of representative sample of papers that have used different pre-training techniques. So kind of the first type of pre-training that we can do on our source data set is called supervised pre-training. So that's following the most popular paradigm of machine learning, which is supervised learning, where your data set will have explicit labels. So this first paper used a pre-trained model called VGG-ish, and that was trained on the audio set data set, which is just audio tracks from YouTube videos. And the task it was trained on was multi-label audio classification, basically audio tagging. This second paper also used audio set, but it used a variety of different CNNs, not just the VGG architecture, and it also did the same, was trained using the same task, the same source task. This third paper is also another supervised pre-trained model, and it's called ResNest, and instead what it was trained on was the ImageNet data set. So which is pretty interesting because we're trying to apply this to audio data, but this pre-trained model was trained on images, so I guess they thought there would be some kind of transfer there. This fourth paper is instead follows a different pre-training paradigm, which is self-supervised learning. So self-supervised learning is when you don't have explicit labels for your data set, but you can kind of come up with labels based on just the input data. And this is very useful when, labeling all of your training samples can be very time consuming and expensive. So if you can kind of come up with a task where the answer, the label is self-evident within the input data itself, that's very useful. So in this one, they used mask acoustic modeling, which is basically they would mask certain parts of the mel spectrogram, and they would get the model to try to guess what was there. So this was trained on the Libri speech dataset, and it's called Mockingjay. And finally, this one is another self-supervised pre-trained model. It was trained on the Coswara dataset, which is an actual COVID-19 dataset, whereas all of these so far have been more general purpose datasets. And its task was, it's called contrastive representation learning, where basically what you do is you come up with a definition for every single pair of training samples. You define whether or not it has a positive or negative relationship, and this model would then try to come up with a representation for each training sample such that positive samples are closer together and negative samples are further apart based on some sort of similarity metric. Cool. So that was pre-training. That was quite a bit. Next, we've got to cover adaptation. So we've got this pre-trained model that's gained some knowledge from an adjacent data set, but now we're trying to adapt that to our actual target task, the task that we're interested in. So for this first paper, the way there's kind of two types of adaptation methods that you can use. So first is feature extraction, which is where you use the pre-trained model only to represent the data in a better way, and you would freeze all of the parameters of that pre-trained model during the adaptation phase. So that's what this first paper did, and that's what these first three papers did. But these bottom two follow what's called a fine-tuning approach, which is where you've got your pre-trained model, but during the adaptation phase, you would also update the parameters of these pre-trained layers as well. Cool. And kind of to cap it off, I wanted to talk about general purpose pre-trained models. So far, the way we frame these pre-trained models is that we have a target task that we're interested in, and then our pre-trained model is just to kind of in service of that particular task. But we can kind of invert our thinking and look at general purpose pre-trained models that have been very, very popular and very successful in recent years in machine learning. So these pre-trained models are not built for one particular pre-trained task, one particular target task. They're built such that they would be useful for many different downstream tasks during the adaptation phase. So two very famous models of these general purpose models are Bert, which came from Google, and GPT-3, which came from OpenAI. So these are sometimes termed foundation models because the intention is that these serve as the foundation for, or the basis for many different models doing many different tasks. Cool. And another type of pre-training that I found was what's called domain-specific pre-training, which is Bert and GPT-3, they're trained on very broad data. So they're NLP models. They're basically trained on all text on the internet. But researchers have found that if you pre-train on a more specific domain, you can actually improve performance. So this first paper pre-trained a model from scratch just on medical corpus, medical documents, and it was found to perform better than a general purpose pre-trained model. And this one, BioBert, uses a paradigm called continuous pre-training, where it started off with the Bert model, but it was then further pre-trained on a corpus of medical documents, which again showed improved performance for tasks involving medical documents. Cool. So that was my literature review, and kind of the research gap that I've kind of found is that transfer learning has been used a lot in ARSA systems, but they've been, again, used for very specific tasks. What I'm trying to do, going back to the title of my thesis, it's a self-supervised foundation for ARSA systems. So what I'm trying to do is to build a pre-trained model that can it was inspired by those foundation models. It's a general purpose model that is useful for all tasks in ARSA. So kind of my project plan first is to explore domain-specific pre-training, which is building a pre-trained model specifically on an ARSA dataset. Another one could be continual pre-training, which is I'll start off with a model trained on general audio, but then I'll further pre-train it on like respiratory sounds. And one issue with ARSA again is that there's not a lot of data. So what would be useful is if we could combine a lot of these different data sets and use it to train a pre-trained model. And finally, if I have time, it would be good to be able to build an end-to-end ARSA systems, you know, a smartphone app that performs a variety of tasks. So again, to kind of just summarize, my plan is to build a general purpose pre-trained model that is useful for all of the different tasks within ARSA. So not just disease detection, but also, you know, cough segmentation, severity, classification, stuff like that. Next, I've kind of outlined the necessary skills I need for this project. So first is audio signal processing. This is kind of, you know, feature engineering, like, and learning to use audio processing libraries, you know, to build our MEL spectrograms, stuff like that. So there's libraries like Librosa or Torch Audio that I would need to learn. Next is machine learning. So both machine learning and deep learning have been used in RSA systems. So to be able to compare the two, I think it would be useful to use both scikit-learn and PyTorch. And finally, if I were to build an end-to-end app, then I would need to learn a bit of mobile development. So React Native can be used for that. And because these are machine learning models, it would be good to also be able to deploy these on edge devices, and we could use PyTorch Mobile for that. And finally, this is kind of my timeline that I've set out. So right now, this is T3 2022. I'm currently doing my literature review, and that's coming up to the end of that. Right after that, I'm going to start actually diving in and doing some coding. So I think the first thing that I want to do is to kind of pick a bunch of tasks that I want to benchmark on, you know, see what the state of the art is for COVID-19 detection, cough segmentation, and just kind of pick my targets and build pipelines to be able to evaluate models against those. Then I would have a huge phase during T1 of 2023 where I would experiment with a lot of pre-training approaches to see how well they perform on these benchmarks. And then once I'm happy with a general purpose pre-trained model, then I would start building a smartphone app to like deploy this model. And then finally, I would be writing my final report. So the smartphone app is I've put in orange because it's more of a if time permits. And yeah, that is my presentation. Again, if you have any questions, feel free to leave a comment. Thanks.